Thank you very much. So indeed, there are lots of different kinds of dimensions, and one of the advantages of this Lapidus complex dimension is infinitely many associated with just one system. Who could ask for more than that? Let me begin by thanking the organizers for the invitation to be here, and say it's very nice to be in Budapest again. Yeah, so the title involves 3 objects. My hope is not to get through all of them. I'm hoping to get through a discussion of Lapidus complex dimensions. Maybe with some luck, I'll say something about Borthwick zeros, which haven't got a lot to do with fractal geometry, but they look kind of similar. And with real luck, I won't say anything about resonances. This is my plan. If I mistime it, I may have to. That's life. Okay. So that's the kind of plan, and so it involves, as it says, iterated function schemes, limit sets, stuff like that. Some zeta functions in a fairly benign form, they're not complicated, and also it has lots of pictures. Besides this picture of Warwick, which is not particularly nice, but it's the one I've got available. And so the word confection is, of course, a pun, because I'm going to hand out chocolate at the beginning, in order to distract people from the lack of mathematics that will take place later. So Balázs has to figure out how to open the box, whose dimension is easier to work out, and distribute them by some means he thinks appropriate. Okay, so this is the plan. So let me try to just summarize it on the next slide. So the idea is that you've got some object, some fractal, and in this case, it will simply be some Cantor set living inside the real line. And then you associate to this a bunch of values. These values are actually complex numbers. And here is a plot for some particular example of these complex numbers associated to some particular set. And somewhere in this picture, there would be a 0, probably down here, which corresponds to the box dimension of the particular Cantor set. I'll say a bit more about that later. And they come via these mysterious looking zeta functions. So these will look mysterious when I define them. So they turn out to be poles of this complex function. So we have a set X, we associate some complex function, we look at its poles, and that's what we get. And here is a plot on the left of the poles for some particular example, which I'll talk about a bit later. Okay, that's what complex dimensions are. So Borthwick zeros are slightly different. They're not associated with Cantor sets or fractal sets. They're associated to smooth surfaces, actually of constant curvature -1. And in that case, you associate another zeta function, which has been knocking around since 1956. And this zeta function also has, well, it hasn't got poles, it's only got zeros. And you can plot these guys as well. And these are the so-called Borthwick zeros. And hopefully on the left, there is a plot here. So these are individual zeros for some particular complex function. And this complex function is associated to some surface by some complex function, which is a beta function. So apart from the fact they look kind of similar, not very similar, but they have nice patterns in each case, there is in fact an underlying mechanism in both cases, which leads to similar sorts of results. So we have lots of complex numbers occurring as poles associated to a Cantor set, or if we actually get to it, we have lots of zeros associated to some surface. And that's the main ingredients. And then resonances are something that knocks around in ergodic theory, smooth ergodic theory, dynamical systems, that kind of stuff, which hopefully we won't get to, so I'll just brush that under the carpet, metaphorically. Okay, with a reference to The Sound of Music, the first topic will be complex dimensions. So this is the Lapidus stuff. And so the idea is that we're interested in a Cantor set. So this is my attempt to draw in TIKZ a Cantor set. Cantor set's being difficult to draw. It just looks like a bunch of very small intervals, but let's imagine that it's a Cantor set. And for this Cantor set, I'm interested in the length of the intervals, the countable set of intervals between the points in the set. And I've denoted these by L1, which is meant to be the longest one, and then L2, the next longest, L3, the next longest, in a partial ordering. And then the idea is that we've now got a bunch of numbers. So we started off with our Cantor set. Now we have a decreasing sequence of real numbers associated to it, which is some information. And from that, we want to concoct a complex function. So here we are again. Here's a Cantor set, all these black bits of the Cantor set. The intervals are the red dotted lines, and it's their lengths, which are going to get smaller and smaller and smaller, which we're interested in encoding somehow to give us some sort of information. So far, it's very kind of easy. And the way we encode it is we introduce a complex variable. So formally, we define it as follows. We introduce a complex number, which is S. It might be Z in some places. If you're an analyst, it's sometimes Z. If you're a number theorist, they use S for some reason. It's a classier thing to do, I think. And so you can define this complex function. It's given by this series. It's a bit like a Dirichlet series. And so we're just summing up all the lanes, but raised to some power. And it's the complex power given by S. So it's kind of easy. If you like things like the Riemann zeta function, that would be just raising 1 over n to the power S and summing it. But here, instead, I'm summing up all the lengths of the intervals rather than the reciprocals of the natural numbers for some reason or other. And L is just meant to denote it depends on this collection of lengths. So different Cantor sets, different lengths, different complex function. Okay, so Cantor set, it gave us the lengths. And so if you like, the zeta function is a bit like a generating function. It's just carrying the information in terms of the way it's defined. Okay, and the first observation is that it's going to converge for the real part of S bigger than 1, simply because when S is equal to 1, you're just summing up the lengths of the intervals, and kind of hopefully it's going to be smaller than the size of the diameter of the original Cantor set. So that's why it converges for the real part of S bigger than 1. But it converges somewhere, which is kind of good for complex functions. Otherwise, it's very difficult to do any kind of complex analysis. And there's a very simple way to think of it. So it sums to something which is less than the total length of the interval. And in fact, you can extend it past that. So this tells us that this complex function defined in the lengths of the intervals converges to the right of 1, but maybe it converges on a bigger half plane. And so in that case, we can define D to be the size, the furthest point left, on which it still converges to an analytic function. It converges to something that's got to be an analytic function. So I have my Cantor set, it gives me the intervals. This gives me this complex function. And this is just saying where it makes sense, where it's defined, where it exists. That's just the definition of these things. Okay, let me check my watch. It's a really good thing to do. Okay, so what do we do next? Well, we want to say something about what happens if we extend it any further, probably. Oh, here's an example, even better. So if we go back to the work of Lapidus on this, he was very keen on iterative function schemes, in particular where we have these linear branches. So let's assume that we've got two numbers, alpha and beta. These are the contraction ratios. Maybe R1 and R2 would have been better, but this is a kind of Greek mood at the moment. So it's alpha and beta. And so the affine maps I've defined are just going to be these two guys. And here's a picture. So hopefully it's correct. So 0 goes to 0, 1 goes to alpha under this. And for the second branch, it's just contracting. So maybe 0 goes to 1 minus beta and 1 goes to 1. And so it's just the two branches of this rather simple iterated function scheme. The only information you're putting into it are these two contraction ratios, really. Okay, so this is the simplest kind of iterated function scheme you could think of. Maybe even simpler would be if alpha and beta were equal to 1/3, because then you'd end up with a middle third Cantor set. And of course, the associated Cantor set we're interested in is the limit set for these guys, i.e. it's the smallest, it's the largest. It's a compact set. It satisfies this conditioning of non-empty. And so this is a way to construct our Cantor set X in a very simple way. And as I was saying, if you take alpha and equal to 1/3, then of course you get the simple example, which is the middle third Cantor set. Okay, so this is just a way to construct our Cantor set, for which we can define this zeta function and try to say something about it. And so here's the simplest possible example again. So for the middle third Cantor set, the largest interval, of course, is 1/3. It's a bit you throw away the first time. And then after that, you throw away 2 more intervals of length 1/9. And then after that, you throw away 4 intervals of length 1/27. And then you just keep on going. And so for this very simple example, then the sequence of numbers you get, the sequence of lengths, is just given in this way by this sequence. And so we can just look formally at the definition of the zeta function, which is defined to be taking each of these numbers, raising it to this complex power s, and summing it up. So that's the definition here. And providing that the real part of it is big enough, in this case, log 2 over log 3, we're going to get this thing actually converges. And you can actually compute it. So hopefully, when I sum this guy up, because of the multiplicity, we get this term 2 to the n minus 1, give or take 1 usually. And so if we rearrange it a bit, then possibly we get something a bit like that. Second left of the reader. And so when we sum this guy up, because there's a geometric sum in here somewhere, we get something that looks like that. So this complex function in this case, well, we know it converges to the right by a general result, but in fact, it has a closed form, which of course has an extension to a larger plane. And it looks like that. So in the simplest of simple examples of Cantor sets, this middle third Cantor set, an example of a limit set for a very, very simple iterative function scheme. There is no mystery about this complex function. It's just equal to this quantity. In other cases, it may be more mysterious, but this one is not quite so mysterious. Okay, so what is it good for? Well, it's good for selling books, apparently. So here is a picture of a Lapidus with a book. It says Fractal Zeta Functions and Fractal Drums. It's very expensive, as I remember. That's my only recollection of it. Maybe this is the book sign here. Who can tell? And so this is a picture of the book itself. Very nice yellow color. And here's a picture of another book by Lapidus and his co-author. And in this one, you can actually see the zeros on the cover. Obviously, the publisher thought it was good to put lots of dots on the cover. So here are the zeros for some particular zeta function associated to a particular limit set. And so this is a kind of illustration of these things. And he calls these things complex dimensions. And for those of you who like an endorsement of why these things are important, there's actually a subsection in the book of Kenneth Falconer, which of course is like the Bible. It's endorsed by any section in there. We can only dream of having our results quoted there. Okay, moving on. So here is a picture. So we've done the middle third Cantor set. That wasn't so difficult. And it has an explicit form for the zeta function. So you can actually work out where the poles are. It has a closed form. And so the poles are not so difficult. They just march up this line above the value of d, which in this case is log 2 over log 3, in a straight line off to infinity. So they're not very exciting. But on the other hand, if you take two different contraction rates, alpha and beta, being 1/3 and 1/2, so it's not quite so homogeneous, then in that case, what happens is you go through the same rigmarole. You look at the limit set, you look at the length of the intervals, countable family, you write down this complex function by raising it to the power s and summing, gives you some sort of complex function which has got poles. And in that case, the poles look like this in that particular example. Of course, they also go off to infinity somehow, but unfortunately, the screen is only a finite size, so it's a bit hard to draw them when you get too high. But basically, they look a bit more like that, more exciting than perhaps in this particular case. Okay. And so what does Lapidus prove? Well, let's imagine that we just look at the general case where we just have these two linear affine contractions. then the first observation is, just like in the middle third Cantor set, you still have that there is a meromorphic extension to C. Meromorphic here means it's analytic plus possibly poles. And so basically, he's saying that you take these two contractions, you associate the Cantor set, define the zeta function, and then by this series construction, well, it converges somewhere, but in fact, it extends to the entire complex plane. And moreover, the poles have a very simple form. They're just solutions to this identity. So if you want to know where the poles are for this zeta function associated to the limit set for this iterative function scheme, all you have to do is to look at this closed form expression and look for values of S for which alpha, first contraction rate to the power S, plus beta, second contraction rate to the power S, sums to 1. And that's just a very simple trigonometric polynomial, complex trigonometric polynomial. And in particular, since we know in this case that there's a closed form for the zeros, we get as a corollary some observations, so that if you know that the ratio of log of alpha over log of beta is rational, as it does tend to be in the case where alpha and beta are the same, then the poles are actually periodic in the imaginary direction. You get periodicity. And that's what we saw for the middle third Cantor set. On the other hand, if it's not the case, then what happens is that you get this kind of more confused looking picture. And in particular, there is a pole at the value D, but in fact, there are no other poles on this line above D, but the poles tend to accumulate if you go far enough up in the imaginary direction. Let me go back to the picture. So all it's saying is that there are two cases. If the ratio of log of alpha over log of beta is rational, you get this sort of picture. And if they're irrational, then you get this sort of picture where this guy at the bottom, D, is as far over to the right as you can get a pole. And above that, there are no more poles, but there are poles starting to get closer and closer and closer as you go further up in the imaginary direction. So these are the two features that you get in this very simple construction. I've forgotten if there's anything else at the bottom. Now, that's what it means. So yeah, the poles accumulate. In a sense, you can find poles getting closer and closer in to the line as you go further and further up. Okay. That's so. Okay, so of course, since we look at this formula again, if you look for a real solution to this, that is a solution for a pole on the real axis, then it would have been this value I called D before, which of course is just the box dimension, or if you like, it's also the same as the Hausdorff dimension for these simple examples. And so that motivates the definition of these other guys being called complex dimensions. So one of them is actually a genuine, well-known dimension. The others, who knows, but they are certainly poles for this complex function. So this is just restating Moran's theorem from 1946-ish, which says that the box dimension for these very simple examples satisfies this basic identity. Something I used to teach every year in my fractal geometry course until it was taken away from me, sadly. Maybe I should have made it more exciting. That was probably the error of my ways. So here's a picture of Moran and some curious story about how he had a bad operation at some stage. But has no reference. This has no real relevance to the rest of the talk. I just threw it in because I like to put pictures in occasionally to make it more interesting. So this is part of Moran's story. Okay, so what else could we say about these things? Well, let's try to do something with other examples rather than just affine contractions. And so the next thing you might think about, possibly not, but you might, is where we took the contractions to be inverse branches of the Gauss map, or if you like, we just choose two values, n and m, natural numbers, and we take our contractions to be these values. So 1 over x plus n, or 1 over x plus m. Hopefully n is not equal to m, and then we get some sort of Cantor set, which is the attractor, associated to this sort of nonlinear iterated function scheme. And then we can try and do the same sort of thing. We can say, well, there is a Cantor set naturally associated to these two contractions. And to this Cantor set, we can write down the lengths of the intervals. And then we can associate to that this complex function. And then for this complex function, we can look at the poles. One of them will again be the box dimension or the Hausdorff dimension of the limit set. And the others will contain some information which we may have trouble extracting, but we don't know. So we need to know somehow that these poles exist. And in this case, the best we can do is to say that, well, we don't know, in fact, that this zeta function has an extension to the entire complex plane, but at least it has an extension to a strip. So there's a statement here saying that it converges to the right, like all of these guys. That should be real part of S with an E missing, or maybe it should be a script R if you like that for the real part. So in this example, like in all these examples, it's going to converge to the right of some line. The real part of S is equal to D, which is the dimension, and it has a extension past that line to some width, which you can actually work out somehow. And this width I've just called epsilon. It doesn't have to be small, but it might be. And so the first thing is that it has a simple pole at the dimension. So the dimension appears as one of these poles. And in this case, it has no other poles on the same line, although it will have poles probably to the right of that line. So this is a feature here, which we saw in the second of the examples where we had different contraction rates for the case of the affine map. So this is more, if you like the second case than like the first case. Okay, so we have a new Cantor set just given by two different contractions given by inverse branches of the Gauss map, just with this form, just rational maps. And for that Cantor set, we do the same thing. We write down the intervals, the lengths of the intervals, we sum up the lengths to the power s. It gives us a complex function, and you try to say something intelligent about the poles for this this function. Okay, so here's a picture. So if we take n and m to be 4 and 7, so that's going to be contracting by 1 over x plus 4 and 1 over x plus 7, just an example, then it converges to the right of some line, and the line stops on the axis at the dimension associated to the Cantor set for that. And then the previous lemma says it has an extension past that line as a complex function. And here is a picture. These little dots are the poles of this zeta function, at least in this strip, going up as far as one can reasonably expect to go, and until your computer gets bored, which in this case is an imaginary direction up to 950. And it has a kind of swirling pattern like that. So that's in the case that we take n and m to be 4 and 7 respectively. If you took them to be 4 and 11, why not? You just ask the computer to look at the extension for this this zeta function, and you get another collection of points. Every point here is a pole for the zeta function associated to the Cantor set for the contractions associated to the values associated with contractions 1 over x plus 4 and 1 over x plus 11. So it's a Cantor set. We define the complex function. Again, its dimension of the Cantor set will be on the real axis around about here. And then these are the other poles for this particular Cantor set. So we're just using different values of contractions. We're getting different Cantor sets. And for these Cantor sets, the associated complex function has got different poles. I guess if we take 4 and 5, we get another collection of points that look a bit like this. Or if you choose 2 and 7, it's a bit more higgledy-piggledy. It's a bit like that. Or if you choose 3 and 6, then you get this kind of picture. And you can carry on infinitely often or until you get bored drawing these. So the different contractions corresponding to different pairs of values, different inverse branches, you get different Cantor sets, different zeta functions, and apparently quite different kind of behavior for these poles. Sometimes it's kind of well ordered, whatever that means for individual points in the complex plane, or it's kind of more confused, one of the two. So you might reasonably ask, is there anything you could say in general about each of these examples? Are there common features? They look very different, but maybe they have something in common, something that we could actually state as a theorem, for example. That would be nice. Sorry? It is not periodic, that's true. So in particular, it's not periodic because in each of these examples, B, the dimension of the set, is a pole on the real axis, but it doesn't appear anywhere above that. Everything else has to be slightly further to the left. And as we saw in the affine case, they could get very, very close to that line, but in fact, they never quite reach it. Okay. In the case of where the ratios, the log of alpha, the log of beta is really like log above. Okay. This slide you can kind of ignore, but I throw it in because you might be interested. Somebody might be interested. I'm interested. Okay. In fact, what we do is we don't plot the zeta function as defined before because it doesn't converge very fast. What we do is replace it by another zeta function, which has the same structure, has the same information about poles, but actually converges a bit faster. And so the way that works is that for all finite strings, different combinations of contractions, we can write down associated to this string, this word, we can write down the contraction by composition. So we can do this for any finite string. And then for this finite combination of contractions, it's going to be a fixed point because it's a contraction. So now we've got countably many fixed points associated to countably many strings. And then we write down this rather funny looking complex function here, which involves summing up, the product over all strings of this quantity, which is just the like the absolute value of the multiplier, i.e. the derivative of the map at the fixed point. But the complex variable is crept in here, and k just comes in to make it work, basically. So there's another complex function defined like this in a rather complicated looking way. But the merits of this are that it again converges in some half plane. This one extends to the entire complex plane. And the zeros of this guy actually agree with the poles of the zeta function I defined before. So when I draw these pictures, or more specifically, I instruct some postdoc to draw these pictures, they're not actually drawing the poles for this other zeta function. What they're actually doing is sorting out the zeros for this more complicated guy, and then just using the fact that they have the same property. So the word aside at the top means you should instantly forget what I just said. I will, so you should join me in this fact. Okay. And so what can we say about all of these different examples in the case where we have a Cantor set generated by inverse branches of the Gauss map? Well, there are some common features. So as we were mentioning earlier, in the case where we have linear contractions, where the ratio was, well, there were two possibilities. Either there were poles, it was periodic with poles in the imaginary direction, which wasn't too common, or more typically, you've got these poles marching towards the line. But in fact, that does not happen in these examples. So in the case of these inverse branches to the Gauss map, so the contractions are 1 over n plus x and 1 over m plus x. You look at the Cantor set, you write down the zeta function, you know that it's going to converge to an analytic function to the right of the real part of S is equal to D, the dimension of the Cantor set, and you know that the poles, when they exist, will therefore have to be to the left of that line. But aside from this guy, the pole which will always exist on the real axis, there's a gap. So however far you go up in the imaginary direction, within delta of this value, you will not find any more poles. So this was a phenomenon which is different to what happened in the case of the affine maps. So it's a kind of structural thing that says that when you plot the poles, then there's always going to be this kind of gap which happens here. And it's somewhat pretentiously referred to as a Riemann hypothesis property, because the Riemann hypothesis, of course, is something about the Riemann zeta function, which is not here at all, it's somewhere else. But in that case, the Riemann hypothesis is about not finding zeros or poles, not many poles in that case, not finding zeros in some strip like this. And it's the same sort of phenomena, But in this case, you can actually prove something. And in this case, it's not quite so difficult. So that's the first sort of thing. And as it says here, this property didn't hold for the original affine examples because either in the affine case, they would hold periodic in this direction, which was not the common case, or alternatively, the poles did accumulate on that one. So it's a different sort of behavior to the other cases. And a second property is the following. Well, if you remember the pictures, each of in these swirling patterns, all the points were poles for the zeta function, and you can ask how they're kind of distributed in the vertical direction. Do they get denser as you go further up? Do they thin out? And one way to kind of quantify that is to do the following. So we have all our dots hanging around, all our poles hanging around. So we can take a box, which is going to have a fixed width. So we start at the point D, to the right of D, there are no poles. We go to the left for some distance delta, and this delta should be, well, it should be where we actually have an extension, or it doesn't make sense, but we don't want to go further than D over 2. So it's got a certain fixed width. And then the idea is that we'll take the height to be increasing. The height's going to be T, and as T increases, we count the number of poles that we spot inside this box. So we want to know something about the distribution of these complex zeros, the poles for the zeta function associated to your Cantor set, as you go up in this particular box. So this, I've only drawn one box, but the next box would be as T increases, and so it's the same width but increasing height. And then what happens is that the number of poles grows like T to the 1 plus D, where D is the dimension again. So it grows in a controlled way, or at least in a bounded way, as T tends to infinity. Keep an eye on the time. Okay, so it's just another property of these slides. And there's a more complicated theorem which says that you can in fact reduce D as you go further to the left. But since it's kind of hard to take in, let's not linger on that. Oh yeah, so this is also called a wild-type theorem, and the reason for that is because these zeta functions also occur in other contexts. One context is in the context of Riemann surfaces, and in the context of Riemann surfaces, the compact Riemann surfaces, the poles for that zeta function actually correspond to eigenvalues for the Laplacian. And the original result a while was about counting eigenvalues for the Laplacian, which could be interpreted in terms of poles for that zeta function. And the analog of that in this case would be this statement here. So all it's done is and let's just try to explain why it has this kind of funny name, which you can just ignore. And here's a picture of Riemann, who passed away just before the age of 40, which doesn't tell us very much. And here's a picture of him, well, not half of it. Okay, so that's two statements of the result. So you notice there's a hypertext link here, so skip to the end. So this is the first point at which I gave myself an out in case I needed to stop. And the reason for this is because the next topic now appears. So let me venture to say something about Borthwick zeros. So this is slightly further afield, even more further afield than what I've been saying so far. Because this is not connected with a fractal structure, it's another complex function which shares a lot of features with these examples, but which occurs in a slightly different context. So in this context, what happens is that you have well, it's actually a surface of curvature minus 1. One way to think of it is you think of these red dots as being a geodesics on a negatively curved object. And topologically, we're interested in the region between these three disks, so it corresponds to a sphere. You take it like a football, you cut out 3 disjoint disks, and then there's some geometric argument that says you can put a metric of negative curvature on it. Negative curvature is always great if you like smooth ergodic curve. And for this guy, you can also associate a Selberg zeta function. And the way that's defined is the following. For this particular surface, there will be infinitely many closed geodesics winding around like rubber bands around the surface. And if you collect together the lengths of the closed geodesics and you stick them into a symbol-looking formula to one I defined before, so it's a complex function defined enclosing all this information about lengths of closed geodesics on the surface, then you get this kind of complex function. And this one converges into the right of the real part of S is equal to 1, but extends to the entire complex plane. And here is a plot for some example. And for this example, all these points, as soon as you get further away, it looks like the blur of curves, but in fact, they are individual zeros for this particular complex function associated to the lengths of closed geodesics on this surface. And you get these kind of swirling patterns of zeros for this example. It says here, we are interested in the zeros. I'm not sure who we is in this case. Presumably it's a subset of people. So the thing that determines the geometry of the surface and thus determines the lengths of the geodesics, there's only 3 numbers involved, and it's the lengths of these red curves. Different values of lengths of these 3 numbers will give you different surfaces, different lengths of closed geodesics, and consequently, it gives you different zeros for the function. So here are some different examples. These look more and more like curves, but in fact, they are just lots and lots of individual dots, this time colored purple for some reason. And these are just zeros for this complex function associated to different kinds of zeros, different kinds of surfaces, as described before. So is there any connection between this and the stuff I was saying before about the Lapidus complex dimensions, which were also complex values? And the answer is sort of. So there are some results by Frederick North, whose pronunciation of his name I will not check, I'll just keep going. And he showed the following. He showed that, first of all, for these complex functions, for this zeta function, which is associated to the surfaces and their closed geodesics, well, there's again a Riemann hypothesis type thing. So in each of these pictures, there'll be some magic value down here on the real axis, which is as far as you can get to the right. This number, in fact, is a dimension. It's related to the Hausdorff dimension of the limit set for the associated Fuchsian group, but that doesn't really matter. And if you go up the axis, then there's going to be some very tiny strip in which you cannot find any more zeros. It sounds like the theorem I stated before for a different function. And there's also another sort of Weil hypothesis, which says again that if you take some particular interval down here between the dimension and the dimension over 2, and then you look at a rectangle of a certain height, and you let the height tend to infinity, then there's a bound on the number of zeros for this zeta function that you will find inside that region. And so this is another rather similar theorem to the theorem I stated before. So they are different zeta functions in different contexts. One is associated with the lengths of intervals for a Cantor set, and this one is associated to some geometric nonsense. And for this case, they have very similar sort of behavior. And the reason is because the proofs of the theorems I stated before are borrowed from the work of North. It's exactly the same mechanism, just transplanted from one setting to another. You can argue time. Okay. And so here's a picture of Selberg. And as I said, the zeta function was defined in 1956. A bit earlier than that, in fact, in 1948, there was some controversy involving Selberg and a local guy over the proof of the prime number theorem, which was originally proved using zeta functions in 1896 by Hadamard. But in fact, there was an elementary proof, i.e. a proof that didn't use zeta functions, which came out of the work of Selberg and Ergis. But in fact, Selberg published it and got a first medal and things like that. Here's a picture of Borthwick. He started plotting these things for the first time these plots appeared in the geometric setting, and this was in 2013 at a conference in France, as well as seeing for the first time. So Borthwick is at Atlanta, that's where he lives. And so I've had many interesting conversations with Borthwick about the number 36 bus. I've never discussed these zeros with him, but we used to catch the same bus when I visited Atlanta. For those of you interested in such things, this tie I brought in Atlanta. It's an American style tie because it's very long in both ends. You should always learn something useful. And here's a picture of Frederick North to prove his original results for these Borthwick zeros. I will skip this bit because I don't want to waste time. All this is saying that if you choose all the lengths to be the same and very long, then the pictures of the zeros look like this. And in this particular case, you can actually say what these curves seem to be with a formula for them like this. But that's an accident of the fact that it's a very special case, and it's actually possible to prove something. In general, it's a bit too messy to prove very much. So I have achieved my main aim, which is not to get as far as recommended. But let me just say the following, that the theme here was that these complex dimensions, which were studied by Lapidus, associated with a complex function, a zeta function, for the length of intervals for a Cantor set, have a lot in common with this more geometric object. At least you can prove similar sorts of results. And so the merit of this is that you can actually study something without having to bother to learn any Riemannian geometry. It's easy to explain what the lengths of intervals are. It's a bit harder to explain what a metric of negative curvature is and stuff like that to undergraduates who don't know any geometry, for example. I'm sure here they know a lot of geometry, but in England they know essentially nothing. And in fact, but the analogy doesn't tell us very much about the actual patterns beyond the two features I mentioned, that if you don't get them accumulated on a line, or you get a bound on no growth. The individual patterns, it's much harder in the case of the Lapidus zeros to come up with any intelligent conclusions. What seems to happen is that if you look at these inverse branches of the Gauss map, the ones we were studying, then in fact the zeta function has some similarity to one example of a Cantor set associated to these linear contractions, alpha and beta, because in this case, the alpha and the beta get forced to be chosen to be these particular values. These particular values are simply the weights associated, you know, with the calculation correctly. These are the weights associated to the two fixed points. You look at the derivative of the maps, and they just correspond to having infinite continuous fraction expansions, 1 or 2. Oh, sorry, m or n in that particular case. And so the pictures there are kind of similar. So it's kind of a consequence of what happens in that particular case. And I may attempt radically to see if this hypertext works or not. So that takes us to the end. Thank you very much.